Hi, good morning. Today I'll be presenting our work on applying the fundamental principles of statics and mechanics of materials to a very practical biomedical problem: injury prevention in the barbell squat. Let me begin with a brief abstract of our study. Our objective was to apply the principle of statics and materials to model and quantify injury risk during a barbell squat. To do this, we constructed a 1 to 10 scale physical model of a lifter and barbell and performed a complete mechanical analysis. This included solving for static equilibrium, locating the system's centroid, and calculating internal moments and shear forces. Our key findings was that a forward shift of the body's centroid, which mimics poor lifting form, dramatically increases the bending stress on the spine and the shear force on the knee. Okay, now let's look at the why behind this work. The barbell squat is a cornerstone of strength training. While incredibly effective, it carries a significant risk of injury, particularly to the lower back and knees. When technique when technique fails. A proper technique fails. Currently, most injury prevention relies on qualitative coaching advice. We hear cues like "don't let your knees cave in" or "keep your chest up." But what's often missing is a clear quantitative model that shows why these cues matter from a force perspective. And this is where our injury engineering perspective comes in. We start with a core hypothesis that the human body under a barbell is mechanically a loaded structure. Injuries like herniated discs or torn ligaments are fundamentally material failures. They happen when internal stress exceeds the tissue strength. Therefore, the tools we use to analyze beams and trusses, statics and mechanics of materials, should be perfectly suited to analyze a lifter. They should allow us to model the system, calculate the hidden internal force, and explain engineering risk through physics.
Hello everyone, my name is Muhammad Ilzam and I will talk about our methodology for this project. So first, let's talk about our model development. So our model is made with a posture of a weightlifter lifting a barbell over his head, over like here, and with a strength up position as you can see over here. In our model development, we make sure that the model fulfills a specific skills compared to the reference. Like, for example, here for the height, we make sure that it fulfills a 1 to 10 model to reference ratio. And as for the mass, we know that mass equals to volume times density, and volume is height cubed. So, in order to get the volume scale, we need to cube the 1 to 10 ratio in order to get a 1 to 1000 molecular reference ratio for the volume. And that's also the same, the mass ratio for the model will gonna be a 1 to 1000 ratio as well. So we already have the scale. Now let's translate it. So as for the body component, we are referencing a person with a height of 138 cm. And so using the 1 to 10 scale that we mentioned earlier, we're gonna get a height for the model of 30.8 centimeter. As for the mass, we know that the ratio is gonna be 1 to 1000. So we're gonna have a referencing a person with a weight of 60 kilogram, and thus the model we're gonna have a mass of 60 gram. As for the barbell itself, we are using a reference of a 70 kilogram barbell, which consists of 30 kilogram plates on each side, and the bar itself, which weighs about 10 kilogram. Therefore, it's going to have a total of 70 kilogram, on which we will translate to a model on a scale with about 70 gram. So for the each weights on the plate will consist of we will make of a 7 stack 20-cent coins, which will form a cylinder with a length of 1.23 centimeters and a diameter of 2.06 centimeters. And for the bar itself, we will be using a pencil which fulfill the mass requirement of 10 gram, a 10 centimeter length, and a diameter of 4 millimeter. So in the end, this over here, as you can see, is our finished model. So we're already finished with the model. Now let's talk more about the analytical procedure. Now let's look into the force measurement and equilibrium analysis. First, The model is going to be analyzed as a static, rigid body. Next, the force. The force they are acting on that includes the weight of the total barbell and the weightlifter himself, plus the normal force that are opposing this force earlier. Next, the centroid. The model is divided into many segments, and the volume and individual center of this segment are going to be calculated based on their respective model geometry. The segment consists of torso, legs, arms, barbell, and also the weights. Next, the stress and strain estimation. First, the rubber shaft is going to be analyzed as a beam in pure bending. Next, the internal forces and the moments at critical anatomical locations, which we will be derived from the force equilibrium analysis beforehand, will going to be used to approximate the normal and shear stresses.
Hi, my name is Hafiz, and I will be presenting my calculations about the equilibrium of force and motion, or force and the moments. Now, in powerlifting, it is a necessity that the barbell is lifted midair and remain that way for a few seconds to display a notion of the limitations of human strength and what we can achieve. But in the static sense, we have to learn how to keep the x forces, y forces, and the moments at a certain equilibrium. So just that, stay in motion, power lifting up until the muscles down the metrics. Now the model mass we have is 60 grams, and so far we are projected to have a 14.5 centimeter rod and a weight diameter of 4 centimeters in terms of the model. But then again, we ended up utilizing coins and a pencil, so the actual size might differ. But anyway, so we got the mass of the barbell on 70 grams and the mass of the dummy 60 grams. Given those figures and the calculation provided by another member of our group, shout out to them, we found that the force of the dumbbell is 0.687 newtons, and model mass, which is 60 grams, it comes to weight, which is equal to 0.589 newtons. Add them up together and add them add them together, and you got 0.6375 newtons in reaction forces. And this also implicates that the force on the hand is 0.343 newtons, as they are holding each the rod, end of the rod are really close to the plates. So the sum of the force on the x direction is zero, so no horizontal forces, and same goes for the y direction, which is which also equates to two reaction forces, which equates to force of the dumbbell plus the weight, and the R equals to 0.6375 newtons. As the moment, I also counted that the reaction forces on the y direction equates to the force in the hand. So the moment equilibrium above the shoulder is equals to moment of shoulder, which equals to force of hand multiplied by length L, which is length of the arm, multiplied by sine of theta. Sine of theta, in which it's the length in the armpits. I mean the angle in the armpits. So in conclusion, in a symmetrical position, the sum of forces on x, y, and the moment have to equal to zero to hold the posture for a certain amount of time. Of course, until the muscle gave way and you have to drop it. Thank you very much.
Okay, hello doctor, it's Longhui Chen here, and I'm here to explain the axial loading on spine and stress and strain in barbell bending. And my matrix number is 25062161. Okay, let's start from the axial loading on spine first. In the reality, when lifting up the barbell, the athlete's body will present a leaning stage in an acceptable extent, which will produce an horizontal distance between the axis of spine and the excess of mass of barbell, like this place. And the distance is called the lever arm, and brings out the following formula. The mass of barbell times lever arm equals to bending moment. Okay, in order to equivalent the moment produced by the bending of the barbell and protecting the body from falling, there will be an extra force produced by the muscles, with an opposite direction and times of magnitude larger than the bending moment. The muscles can be able to maintain the equivalent. But in our model, which is like this, the process might not be that complex. We can even let the figure lifting the barbell without leaning its body, so I'll take it as a simple static problem, which is presented behind. Then comes to our calculation part, the barbell bending. According to our model and the definition of the pure bending, we can consider our load-bearing shaft is experiencing pure bending. And here's the data of our model. The diameter is 4 mm, and the length is 100 mm, which is 10 cm, and the mass of the load is 0.343 Newton, as it can be present like this. Easier for our calculation. Then we need to calculate the bending moment on each side. I'll first take the right side as an example. After measurement, the distance from each hand of the figure to the middle axis is about 3.33 cm, like this place. Okay, then we can calculate the right side moment. Okay, then calculate the moment of inertia, which is the I. Okay, with M and I, we can now get the bending stress, and then the bending strain.
So, hi, I am Abdullah Yasir and I'm going to explain the importance of 3D centroids in biomechanics and how it affects the balance and stability during weightlifting. In biomechanics and sports engineering, the center of the human body is a key factor in understanding posture, force distribution, and injury risk. During lift, the position of centroid changes as the athlete and barbell move. With the centroid shift outside the base of the support, balance is lost and injury risk increase. As we can see on the slides, this is our front view and the side view of our model. The origin was fixed and each segment was analyzed individually. Uh, so the parts, the structure was divided into 14 uh, geometrical segments, which is including rectangular prints used for the legs, torso, and arms, and for triangular prints used for the feet and armpits, cylinders for the bars and weight, and ellipses for the head. So this is the calculation. The table V is the volume for each body part or object. X bar, Y bar, and Z bar. These are the centroid coordinates for each part measured from the reference origin. Uh, and these values are used to compute the weights average when finding the overall centroid. So using the formula that shows on the slide, the centroid is at 6.26 cm and 9.40 cm and 1.31 cm. This point is the balance point of the body and barbell. The centroid falls between the feet so the body is stable. The system is in static equilibrium, and the higher the Y bar value means it less stable to the side fall, which meaning the model is not that stable since the Y value is what you say? Yeah, that's all.
In summary, our analysis yielded one clear mechanical insight: a forward lean, which shifts the body's center of the mass, multiplies the damaging loads on the spine and knees. This confirms that safe lifting is not just about effort, it's an engineering exercise in keeping internal stresses within safe limits. And lastly, our future work. First, in model development, we plan to increase its biological fidelity. This means using advanced materials that mimic the distinct physical phenomena, such as viscoelasticity of real tissues, integrating active muscles forces as internal cables, and scaling up the model with impeded sensors for direct measurements. Second, in analysis, we will move beyond statics. The next step include dynamic analysis to capture momentum effects, introducing cyclic loading to study wear and tear injuries, and creating a parallel computational FEA model for deeper validation. That's it for me. Thank you for your attention.